Jai Hind, my name is Nidhi Singh. I am Assistant Professor in Electrical and Electronics Engineering Department in Ajay Kumar Garg Engineering College. Today I am going to discuss magnetic circuit, which is a topic from Unit 3 from Fundamentals of Electrical Engineering. This is a subject in first year. So, these are the contents of today's lecture. First, we will discuss the definitions which are related to magnetic circuits. Then we will discuss what is magnetic circuits, its type, that is series magnetic circuit and parallel magnetic circuit. And then we will discuss the numericals related to these topics. So, starting with the first definition, that is magnetic field. So, what is magnetic field? Basically, magnet has its influence on the surrounding medium, and the region around the magnet within which the influence of the magnet can be experienced, it is called magnetic field. Now, the next term is magnetic flux. What is magnetic flux? It is basically the total lines of force in magnetic field, and this is called the magnetic flux, and it is the symbol which we use to denote the magnetic flux is the phi, and the unit of this magnetic flux is Weber. Now, the next is magnetic flux density, which we denote with capital B, and this is a magnetic flux density. So, it is basically the magnetic flux which is passing through the unit cross section, and this is its unit is Weber per meter square, and this is phi by A. Now, next is the magnetic field intensity or the magnetizing force. The magnetomotive force per unit length is called the magnetic field intensity, which is denoted with H, and this is F by L, or its unit is ampere turn per meter. Or we can define magnetic field intensity is also determined by the number of turn, the current and the length of the core. So, we can define H as N into I upon L. The flux density and the magnetic field intensity, they are related by the equation B is equal to mu H. Mu is permeability. Next is magnetomotive force. Magnetomotive force is in short we called it as MMF. So, it is basically a driving force which is required to drive the magnetic flux through a magnetic circuit, and the product of N into I is called magnetomotive force, and its unit is ampere turn. So, what is N here? N is basically the number of turn and I is the current. So, the MMF we can define as N into I. The next we have permeability. So, the magnetic conductivity of iron as compared to that of air is called the permeability. And permeability, we have absolute permeability, relative permeability, and so the absolute permeability we denote with mu, and this of a medium is given by B by H, where B is flux density and H is magnetic field strength, and the value of mu can be calculated as mu naught into mu r, where this mu naught is 4 pi into 10 power 7, and mu r is relative permeability. So, mu naught value is 4 pi into 10 power minus 7, and mu r is relative permeability. So, the relative permeability mu r of a medium is given by B by B naught, where H is constant. So, here B is flux density in the medium under consideration, and B naught is flux density in vacuum. And for air or free space or vacuum, the value of this relative permeability is 1, right. So, you should remember that this mu r is always 1 for air, free space or vacuum. Then coming to the reluctance. So, now what is reluctance? In electrical circuit we have resistance. So, what resistance do? Resistance basically it resists the flow of current. In a similar way, this reluctance is basically the resistance to flow of magnetic flux. So, reluctance is the resistance to flow of magnetic flux. So, if by analogy we can compare the magnetic circuit reluctance, which is the existence of the magnetic flux, and this reluctance depends upon the length of material, cross section area of material, and permeability of a material. So, we can define S is equal to L upon mu A, where mu is mu naught into mu R. Now, next we have Ohm's law in electrical and magnetic circuit. So, if we see the Ohm's law in electrical circuit, so we have here electromotive force, we have resistance here and the current flowing in this circuit. So, according to this Ohm's law, we can write V is equal to I into R, right. In a similar way, in magnetic circuit, the Ohm's law in a magnetic circuit, here we can see that here the coil, it produces the magnetomotive force, and because of that we have a flux in this core, and we have some magnetic resistance, right. So, the magnetomotive force is proportional to number of coils winding and strength of the current which is flowing through it. And the magnetic resistance we know is inversely proportional to magnetic permeability, and magnetic permeability of air is much lower than that of magnetic body due to high magnetic resistance of core gap. So, if we relate this magnetomotive force, resistance and flux according to Ohm's law, we can write F is equal to phi into X. So, magnetomotive force is equal to magnetic flux into magnetic resistance. So, S is called here the reluctance. Instead of calling it resistance, we call it reluctance. Then we have permeance. So, permeance, it is the reciprocal of reluctance and is a measure of the case with which the flux can pass through the material, and its unit is Weber per ampere turn. So, it is written as 1 upon S. Like in electrical circuit, we have reciprocal of resistance, we call it as conductance. So, here also we have a permeance which is reciprocal of reluctance. So, reluctance means it resists the flow of flux, but permeance is reciprocal of it. It means it measures, it is the measure by which the flux can pass. Now, we have some comparison between the electric and the magnetic circuit. So, if we compare or we can say the analogy between the electric and the magnetic circuit. So, if we compare, in electrical circuit, the power traced by the current is the electric circuit, right. If we call it as a electric circuit, and in magnetic circuit, it is the path traced by the magnetic flux. It is called magnetic circuit. So, in electrical circuit, if is where the path is traced by the current, right, and in magnetic circuit, path traced by the magnetic flux. Now, next we is the here EMF, that is electromotive force. Electromotive force is the driving force in electric circuit, right, and here the MMF is the driving force in the magnetic circuit. So, EMF unit is volts and the MMF unit is ampere turn, right. And the next analogy is in electrical circuit we have current, right, and it and which unit is ampere. In magnetic circuit, instead of current we have flux and the unit is Weber here. The next, here the flow of electrons decides the current in conductor, and in magnetic circuit the number of magnetic lines of force decides the flux, right. So, here the flow of electrons is deciding the current in the conductor, and here the number of magnetic lines of force deciding the flux. So, in electric circuit we have resistance which opposes the flow of current and unit is ohm, and in magnetic circuit we have reluctance, right. We have already discussed what is reluctance. So, it reluctance and the opposition given by to the magnetic part to the flux, the unit is ampere turn per Weber. So, and here we can define R as resistivity L into A. So, it is directly proportional to the length, inversely proportional to the area, and it depends upon the nature of material. And here we can define S as L upon mu naught A, and where mu naught stands for mu naught into mu r. So basically we can see here that it is directly proportional to the length. Length means the mean length, and inversely proportional to the mu naught, that is permeability, and also inversely proportional to the area of cross section. Then here we have the current we can express as EMF by resistance, and in similar way we can express flux as MMF by reluctance, right? And then here we have a current density, here we have flux density. For electrical circuit, we have Kirchhoff's current law and voltage law, which is applicable for electric circuit, and for magnetic circuit we have Kirchhoff's MMF law and flux law, which is applicable for magnetic circuit. So if we summarize this, we can say in electrical circuit we have current, and in magnetic circuit in place of this current we have flux. Here we have EMF, and here we have MMF, right? In place of EMF in magnetic circuit we have EMF. Then here we have resistance, and here we have reluctance, right? The same nature, here we have resistance and here we have reluctance. So these are the main analogies which we should remember. Now next, there are some dissimilarities between electrical and magnetic circuit. So let's see what are the dissimilarities between the electric and magnetic circuit. So in electric circuit, the current actually flows. Actually flows means there is a movement of electrons. The electrons are actually moving in the electric circuit. But in magnetic circuit, due to MMF, flux gets established and does not flow in the sense in which current flows, right? It gets established, but it is actually not flowing. Like in electric circuit, the electrons are flowing in the circuit. And for electric circuit, we have insulators, right? But for magnetic circuit, we don't have any insulator. So there are many materials which can be used as insulator, like air, PVC, synthetic resin, from which current cannot pass. But there is no magnetic insulator, as flux can pass through all the material, even through the air as well. So magnetic, there is no insulator for the magnetic circuit. It can pass, the flux can pass through the air also. And here energy must be supplied to electric circuit to maintain the flow of current. So energy is required to maintain the flow of current. In this, energy is required to create the magnetic flux, but it is not required to maintain it. Energy is required here to create the magnetic flux, but it is not required to maintain it. Then the next is the resistance and conductivity. They are independent of current density under constant temperature, but many changes due to the temperature here. Here the reluctance, permeance and permeability are dependent on the flux density. Then electric lines of flux are not closed. They are not closed. Why they are not closed? Because they start from positive charge and end on negative charge. We know that current starts from the positive charge and terminates at the negative charge. But in case of magnetic circuit, these magnetic lines of flux are closed lines. And why they are closed line? Because they flow from north pole to south pole externally and from south pole to north pole internally, right? Suppose here if we have a magnet, this is north pole and this is south pole. So externally they flow from the north pole to the south pole. So magnetic lines, they flow from north pole to the south pole externally, but internally they flow from south pole to north pole internally. So you can see that these are the closed lines. So magnetic, these flux lines are the closed lines. So these are the dissimilarities between the electric and magnetic circuit. Now coming to the magnetic circuit, what is magnetic circuit? So magnetic circuit is, it can be defined as the closed path traced by the magnetic lines of force, that is flux, right? So here we can see this is the example of simple magnetic circuit. So here we have a core, magnetic core of permeability mu. Here we can see winding with n number of turns. The current is flowing here. So MMF n into I will be generated here, and because of that we have a magnetic flux line. So flux will be produced here. The mean length of the core, here we can see the cross sectional area. So this is a simple magnetic circuit, right? And the equivalent electrical circuit of this magnetic circuit can be drawn like this. So we know that the MMF can be replaced by the EMF in electrical circuit, and this flux can be replaced with this current, and we know that we have some reluctance of this core, right? Reluctance of this core, which is depending upon the mean length, the cross sectional area, and the permeability, right? Upon these three factors, the reluctance S is depending upon the these three factors. So this reluctance can be replaced by the resistance. So this is the electrical equivalent circuit of this magnetic circuit, right? Now this is also a example of magnetic circuit with air gap, and here we can see that we have a air gap. So here the equivalent magnetic circuit is drawn. The same structure is drawn here. This is the equivalent circuit. So here we can see here N into I means here the MMF will be generated. So here this Ni is represented. Then some flux is established in this core. So here it is represented with phi. Then the reluctance of this core and the air gap will be different. So both the reluctance of the core and the air gap is shown in this circuit. So this is the equivalent magnetic circuit. In a similar way, you can draw the electrical circuit also. So you will show the two resistances, right? Why two resistances? Here you will show E. Here instead of this flux you can show the current, and two resistances, resistance 1 or R2, R1, R2, because here we have two reluctances for the core and the air gap. Then coming to the classification of magnetic circuit. So magnetic circuit can be subdivided into series magnetic circuit and parallel magnetic circuit, right? We can divide it into series and parallel magnetic circuit. So here you can see the circuit for series magnetic circuit. This is the series magnetic circuit. In series magnetic circuits, the flux will be same. The flux will be same. Like in series electrical circuit, current is same in the circuit, and the equivalent circuit of this equivalent electrical circuit of this magnetic circuit is drawn here. So here N into I is MMF. So here we have E, then flux is represented with current, then Ri and Rg. Ri, the resistance of this ring, right, iron ring, and there will be some reluctance of this air gap. So two resistance are shown here. And now this is the example of parallel circuit. Parallel circuit, if we talk about the parallel electrical circuit, right? If we talk about the parallel electrical circuit, suppose two resistances are here, and the supply is connected like this. So the current will get divided. So if the total current is I here, so I1 and I2, right? The current will get divided. So if current divide means these two branches are in parallel. In a similar way, the flux which is produced here is getting divided into these two limbs. So this is a parallel magnetic circuit. So the equivalent circuit, equivalent electrical circuit is drawn here. So in middle branch you can see the coil. So MMF will be replaced with the EMF. Then there will be some reluctance of this middle path. There will be some reluctance of this middle path. So it is represented as the resistance here, because in middle path we have the core and the air gap. So the total resistance Rg plus Ri is written here. Then we have some reluctance of this side limb also, right? These side limbs also. So it is represented here, the reluctance is represented here as a resistance. The flux will get divided in the side limbs, so I1 and I2, right. So if the reluctance of the side limbs are same, so flux will be divided equally. Like if we have resistance R here and R1 and R2. So if R1 is equal to R2, what will happen? This I1 will also equal to I2, and this is equal to half of the total current, right? If this is a total current. So I1 and I2 will be, both current will be equal and it will be the half of the total current. In a similar way, the flux will also get divided equally if the reluctance of both the path is same. So, series magnetic circuit. So, series magnetic circuit, how we can define series magnetic circuit? Practically, the magnetic circuits, they are basically formed by more than one material with different permeability, and such material can have various length and cross sectional area, and this circuit is called as a composite circuit, right, because it is made up of different types of material. So when those materials are connected one after another to form magnetic circuit, it is called series magnetic circuit. So in series magnetic circuit, the flux is same in all section, right? Flux will be same in all section, and if there is any leakage flux, we will neglect it, right? And flux density and reluctance in each section may vary depending upon the effective cross sectional area and the material. And the equivalent resistance reluctance is the sum of reluctance of different parts of elements. So in series magnetic circuit, as it is if it is made up of different materials, so we will calculate the reluctance of each material and we will sum it up, like in electrical circuit we do, right? If we have a series electrical circuit, so suppose we have three resistances in series, R1, R2, R3. So to find the total resistance, what we do, we add all these resistances, right? In a similar way, in a magnetic circuit also, we will calculate the reluctance of each material and then we'll sum it up. So the equivalent reluctance is the sum of reluctance of different parts or elements. Then the resultant MMF is the sum of MMFs in each individual parts or elements. Like suppose here, this is a composite series circuit. So here we can see if we see this part, right? If we see this part, so we can see that the area of cross section and length compared to this section, right? If we see this, right? So here we can see that these three materials are combined and the length and the area of cross section are different. So reluctance will be different. So first we know the relation between the reluctance, MMF and the flux. We know that MMF is equal to phi into S, and first we have to calculate this S. So S, every section has different reluctance. So first we will calculate, this will be, instead of writing as, I will write it ST. ST means total reluctance. So ST will be equal to S1 plus S2 plus S3, right? So where this S1 will be equal to, here the area of cross section is A1, length is L1. So I can write it here as L1 by mu by A1, right? And similarly S2 will be equal to, length is L2, area of cross section is A2, so this will be L2 by mu A2, and similarly S3 can be written as L3 by mu A3. So S1 plus S2 plus S3 will give you the total reluctance, and after putting this value here and multiplying with the flux, you will get the total MMF. So now coming to the example of this is example of series magnetic circuit. So the question is, a circular iron ring of mean diameter 25 centimeter. There is a circular ring, the mean diameter is 25 centimeter and cross sectional area 9 centimeter square, is wound with a coil of 100 turns and carries a current of 1.5 ampere, and the relative permeability of iron is given 2000. So you have to calculate the amount of flux produced in the ring. So first we will see the diagram for this example. So here we can see this is a ring with a mean diameter of 25 centimeter, which is given in the question, and the area of cross section is 9 centimeter square. Then the coil with N is equal to 100, the current which is flowing through this is 1.5 ampere. The relative permeability is given of this material is 2000. So we have to calculate the amount of flux which is produced in the ring. So we know the relation between the MMF is equal to phi into S, right? So MMF is nothing but N into I is equal to phi into S, and how will you find this S? S is equal to L upon mu naught mu R A. So N is known means 100, number of turn is 100, current is known which is 1.5 ampere, then you have to find the amount of flux, right? So this flux we need to find it out. S, for finding out S we need mean length, right? The diameter is given, so the mean length is 2 pi r, right? 2 pi r, or you can write 2d or mu naught, you know, 4 pi into 10 power minus 7. Mu r is given, that is 2000, and area of cross section is also given, that is 9 centimeter square. So putting all these values we can find the amount of flux. So first calculating the mean length. So mean length pi into d. So if you calculate, this will be in, and converting it into meter, the mean length is 0.785. Then we will calculate the flux. We know this relation MMF by reluctance. We know MMF is N into I. Putting all these values, then L upon, and reluctance is L upon mu naught mu RA. So putting all these values, you will get 0.431 milliweber. So this is the value for the flux. Now coming to the second example, here a rectangular shape iron core has an air gap of 0.01 centimeter. The mean length of flux path iron is 39.99 centimeter. The relative permeability of iron is 2000. The coil has 1000 turns. The cross sectional area of the core is 9 centimeter square. You have to calculate the current required to produce a flux of 1 milliweber in the core. Again, this is a question from series magnetic circuit. So first we will draw the circuit. So this is the required circuit. What is given? The rectangular shape iron core has an air gap of, so this air gap is of 0.01 centimeter, right? And the mean length of the flux path. So this mean length of this flux path, this is equal to 39.99 centimeter. This mean length is given as 39.99 centimeter. The relative permeability is 2000 here, and the coil has the number of turn, this is equal to 1000. The cross sectional area, of this is 9 centimeter square, right? So you have to find the current which is required to produce the flux of. So if you see, the flux is also given, which is 1 milliweber. So again the same relation will be used here. We know MMF is equal to flux into reluctance, right? So first we have to find the reluctance. So here we can see that we have iron core and this air gap. So there will be two reluctance, right? So reluctance of iron path and reluctance of air gap. This will give the total reluctance of the flux path. So first we will calculate this reluctance. So substituting all the values, we know the length of this iron core is given 39.09, and the length of air gap is given 0.01. So 10 power minus 2, we will put all the values in meters here. Then mu naught is 4 pi into 10 power minus 7, mu r 2000 is given, and the area of cross section 9 into 10 power minus 4. And for air, we know that mu r will be equal to 1. So only mu naught is here. So the total reluctance, you will get the total reluctance. So we know this relation, right? Phi is equal to Ni by S. And we have to calculate the I. So putting all the values, you will get 0.26 ampere here. Now coming to the next example, and this question is from parallel magnetic circuit. So the magnetic circuit here, a magnetic circuit is having its winding on its central limb. The cross sectional area of the central limb is 10 centimeter square, whereas cross sectional area of the outer limb, this is the outer limb here, is 5 centimeter square. The effective length of central limb is 16 centimeter and the outer limb is 25 centimeter. Calculate the current required to flow through the winding, which has here the winding turns are 1000 turns, to produce a flux of 1.2 milliweber in the central limb. Now assume that for flux density of 1.2 milliweber, the magnetizing force requires 750 ampere turn per meter. So, and you have to draw the equivalent electrical circuit for this question. So first we will draw the equivalent electrical circuit for this. So the circuit of magnetic circuit is this, where all the cross sectional area and the length is mentioned here, right? So if we draw the equivalent electric circuit, so we know the MMF will be replaced with E. There will be some reluctance of the this central limb. So this will be the reluctance will be represented with the resistance. Now there will be some reluctance of this side limbs, right? So here it is represented with the resistance, and here you can see that the reluctance of these side limbs will be same because the nature of material is same, the length is same, the area of cross section is same. So the flux will be equally divided in both the limbs. So here this I, here it is in this branch, this is written I by 2, this is written I by 2, because these resistances are equal as the reluctance of both the side limbs are equal, right? So now coming to the solution part. So here the flux density of central limb, we can find the flux density of central limb, which is phi upon A, right, which is coming 1.2 Weber per meter square. So flux density in outer limb, it will be same as that in the central limb, since since half the flux is available in each of the outer limb and the cross sectional area is also half of that of the central limb. So here it is coming 1.2 Weber per meter square. Now the corresponding H for flux density 1.2 Weber per meter square, it is already given in question, is 750. So the total MMF required will be equal to MMF required for central limb plus MMF required for one outer limb. Only one outer limb will be considered, right? Why? Suppose if you want to write the equation for E is equal to, so you will consider E. You will consider E is equal to I into RC plus I by 2 into R naught. Either you will consider this loop or you will consider this loop. Only one branch will be considered with this central ones. In a similar way, in magnetic circuit also, with the central limb, you will consider either any one outer limb. So since H is equal to, we know this relation MMF by L. So total MMF can be you can find the total MMF here. Then the total MMF, you can write all the values. So the current, you can calculate the current as I as 0.3075 ampere, right? So this is how you can find the current here. So these are the references for this lecture. I have referred the D.P. Kothari and S.K. Bhattacharya for the numericals. So that's all.